Okay. Greetings, everyone. Welcome in to my channel. I am Professor L, and this is a live stream for math tutoring. So this is open to the public. So if anyone is out there and they need help with math, then you're welcome to put a problem in the chat, and I will do my very best to work the problem out for you. But if you don't have a question, then I'm just going to be discussing the exponential function and analyzing the graph. I started working on this function this past Friday, and my live stream crashed about 15 minutes in is when I noticed it, and then I think that it ended up being about 12 minutes long. Very short video on Friday. So we'll go ahead and continue talking about the exponential function tonight. And so happy Monday, and I hope that everyone is doing well. And come join me and do some math. So the exponential function is in this form. F of x equals a to the b of x raised to the x. And the a in this case is the it is the vertical stretch, but in an exponential function, what happens when you stretch it, it affects the y-intercept. So the a ends up being in the transformation in the graph, the a ends up being the y-intercept, and the b value here, b is basically stands for base, and I don't know if they picked that on purpose or who decided that, but coincidentally b stands for base in this case. And of course, x is your variable. It's your independent variable. So we have, and then also put this up here, we have y equals f of x. So we can just interchange y and f of x essentially. And we were looking at, basically, we sketched some points here. And these are the points of the graph that was producing. And we noticed that this function only exists in the first and second quadrant. I'm gonna sneeze, sorry. I knew I was gonna do that. Bless me. Okay. All right. Anyways, what was I? Lost my train of thought here. That's up here. All right. I completely forgot what I was talking about. It's okay. So the exponential function, notice that it's only existing in quadrant 1 and 2. And in quadrant 1 and 2, we have the domain is positive and our range is both positive. And in the second quadrant, we have a negative domain, and then we have a positive range. So what you're doing is you're feeding it. I got a little crazy. But what we're doing is when you're feeding it negatives, you're still getting a positive value. And notice here, negative infinity, you're approaching the 0 line, but it's never going to touch 0. So y, no matter what value you give it, positive or negative in here in the domain, it's going to generate you a positive value. And we saw that here when we were giving it some negatives. and it was leading to fractional exponents. So what I want to do is I want to show what happens because we have a situation here where our base is greater than 0. But what happens to the graph when you put your base? So this is for b greater than 0 here. What happens when 0 is, let's see, b is greater than 0. Hang on. Wait a second. Is less than 0 is less than 1. So when b is between 0 and 1, what happens to this function? So what I'm talking about specifically are those values on the number line between 0 and 1. So we have 1/2, 3/4, 2/3. Why did I write 2/3? All right. But we have 3/4. This one would be 1/4, and so on and so forth. We're talking about fractions between 0 and 1. So we're going to erase these computations, and we're going to make a new table and a new function. And we're going to look at when our function f of x has a different size base. So we'll go ahead and leave a at 1, and we'll say what's going on at 1/2 x. What about 1/2 x? And we're going to look at the same point. So we'll go ahead and start with -2. -1, 0, 1, and 2. Because this is what we did for the first graph. And we can switch these around here. You can say -2, -1, 0, 1, and 2. And then switch them around. And we saw -1/2 was 1/4. -1 was 1/2. 0 was 1. 1 was 2, and 2 was 4 on this one. So let's see what happens plugging in these same values into 1/2 x. So in this case, a equal 1 and b is going to equal 1/2. Your base is 1/2. And so we've got, let's see. Look at me using all kinds of important stuff off. Equal signs. 1/2. Okay. So f of 1/2, or -2. Let's do 0 first. It's negative numbers. Let's start off with something that's easy to calculate. 0, -1, and 1 are the easiest ones. So we're going to start here in the middle. We'll say 1/2 raised to the 0 power. Anything raised to the 0 power is the quantity 1. I already proved that in the last video. Pretty sure that made it through the video. Anyway, when you subtract, when you multiply, anything divided by itself essentially is equal to 1. And I really don't want to waste the time to show that again, but I'll have to look back in the video. All right, -1 now. F of -1 is going to be 1/2. Oh, wait. We're not going to do -1. We're going to do +1. So 1/2, just plugging in 1 where x is. 1/2 to the first power is just 1/2. So we'll say that's 1/2. And then the other positive number we have on our picked in our domain is 2. So we'll say f of 2. And we're going to raise 1/2 to the second power. Now, when you do that, you have to make sure that when you do that, let's see, when you square a fraction, you're going to square the numerator and you're squaring the denominator. So you just have to square both. But 1 squared is just 1. And then 2 squared is 4. So f of 2 is 1/4. And we'll go back to our negatives now. So f of -1, I just like to do the easy part first. 1/2 to the -1 now. 1/2 to the -1. Now we have to remember those negative exponent rules, and a parentheses might help us in this at this point. So we have that 1/2. What we're doing is, let's see, 1 gets raised to the -1/2, and 2 also gets raised to the -1. They're both getting raised to that -1 power, and when you do that, the 1 goes to the denominator and the 2 comes to the numerator. So that becomes 2/1 when you simplify that. So that's going to be 2. Okay. And then we've got one more to evaluate, this this f of -2 here. So let's just do that one so we have a symmetrical graph and we see the difference in these functions. So the 1/2 now raised to the -2 is the same thing. We've got 1 raised to the -2, and then we've got 2 raised to the -2. So now we're just going to switch. It becomes 2 squared over 1 squared. And then that is going to be 4. 1 squared is 1. So now we have this point on there, 4. And do you notice that these two tables are almost exactly the same, only the ranges are flipped? And this is what this base does. So what happens is, if b is greater than 0, you have an increasing function, and these are the growth models. So if it's b is greater than 0, you have a growth. And you can see that because this graph right here, as your graph is moving, you start out with an initial value of 1, and as your graph is moving to the right, to the positive direction, also your y values are also moving to positive infinity. And if you have both values going to positive infinity, as your graph is moving from left to right, you have an increasing function, and an exponential function in this case would be a growth, because the exponential function is primary application rather would be some sort of growth, growth in money, growing in bacteria, growing in if there's an outbreak in reproduction of bacteria, or any type of modeling any type of tree growth or anything, growth of populations. The exponential model for growth for this one would be is greater than 0, or greater than 0, actually it's greater than 1. My bad, I have to make sure that I say that correctly, because if it's between 0 and 1, you have a different situation, you have a decay. So for b greater than 1, if it's 1, it's still a decay. Okay, 1 to the x, and we can verify that. So if it's greater than 1, you have a growth. If it's between 0 and 1, you have a decay. And we're going to see that as soon as we sketch the graph of this function right here. So we're going to go ahead and put these points on there. We have -2, 4. So -2, 4 is up here. And then we have -1, 2. So -1, 2. 0, 1 is on there. So we have those points in common. 1, 1/2. And 2, 1/4. And so what's happening is you have this type of situation. This is what this function is doing in the graph. And it's going from, let's see. And as you are increasing, do you see how your x values are increasing? You're going to positive infinity in the, as far as your x values, but your y values are going to 0. Okay. We're not going negative down here yet, but what's happening, and this is f of x. So this one was f of x equal 2 to the x. This one is f of x equal 1/2 x. Okay. Let's see what's happening. So this one is a decay, and this one is a growth. All right, good. And let's see here, what else I want to say about this exponential function. So the shifting of this graph, so those translations. Okay, if a is negative, let's see what happens to this graph. A goes negative. And we can take these same 4 points, -2, -1, 0, 1, and 2, and we can reflect that graph. F of x equals negative 2 to the x. Do that one. So what we're doing is we're taking all of these points and we're making them negative. So that first one, f of -2, is going to be 2. Where's my function? 2 to the, hold on, that's -2 to the 2. -2 to the -2 power. So that equals -1/2 squared, which equals -1/4. And then same. So we're going to go ahead and just copy all of these points and just put negative. So it's -1/2 -1, 1, -2, and 2, -4 for that function. So what's happening is if A is negative here, then you have this going on. We've got 1, 2, 3, 4. So that'll be half, and then that'll be a fourth. So I've got -1, -2. So at -2, we're at -1/4, which is right here. And then at -1, we're at a half, which is right here. And then 0, we're at -1. And then at 1, we're at -2. And then at yeah, 1 at -2, hang on. And then 2, we're at -4. Okay. So we've got this thing going on. So this would no longer represent a growth, because this is now a decreasing function, but it's an exact reflection. So this one is, we'll label it f of x equals -2 to the x. Okay. And then we've got one more graph to sketch. We're gonna sketch. So we have, let's box them. We have f of x equals 2 to the x here. F of x 1/2 x. This is, here, I'm gonna fix this one. F of x -2 to the x. And then we're going to do one more. We'll put it, where should we put it? Let's see if we can squeeze it in here. F of x equals -1/2 x. That's a linear function. Raised to the x, it's got to be an exponent. We have x comma y, -2, -1, 0, 1, and 2. See if we can sneak it in here. And then what we're doing is we're taking all of these values here, this function, and all we're doing is calculating them the same. However, we're going to put a negative out here. So it's negative. I'm copying this range because I don't need to recalculate those values. You can do the first one just to prove it. F of -2 equals -1/2 of -2, which equals negative. We're going to reciprocate both of those. So that becomes 2 squared over 1 squared, which equals -4 over 1. So that's 4. So it's going to be -2, -1, -1/2, and -1/4. Let's sneak it in there. And then we'll go ahead and plot that graph here. We can see the manipulation of this exponential function. And I mentioned that this exponential function is the inverse to the logarithm. So now I have to talk about logs, the logarithmic function. So I'll probably talk about that one next. All right, where are we? Okay, so we've got -2 2, -4. -2, -4 down here now. And we've got -1, -2, 0, -1 is on there. 1, comma, -half is here. And then we've got 2, comma, -1/4 is here. All right, so we've got this one now. We've got that. If you could imagine that this graph here, this 1/2 x is just been reflected about the x-axis. So it's just been flipped. And that's what that negative is doing when a is less than 1. Okay. So here, a equal -1. And here, b equal 1/2, a equal -1. Here, a is positive, and then here, a is also positive. Okay, all right. And see, almost 30 minutes. And no students for no math questions. So, okay, that's a tough one. I might go ahead and stop here. Could go ahead and list the domain and range real quick of these functions. So, if you notice on the graph of, so the domain will just be the same for all these functions. It's negative infinity to positive infinity. The range is kind of restricted on these a little bit. So the domain of all these functions, we can say all of the exponential functions anyway, you have a domain where there's no restriction. There's no asymptote. There's nowhere the graph is not going to exist. You can plug in all real numbers into the domain of the exponential function, and you can you will get a real number in return. However, the range, let's see, is going to be restricted because so the range is going to be, and you've got that asymptote, and we're going to have to talk about it, okay? Because typically the range is parentheses 0, comma, positive infinity, or we'll say negative infinity to 0. Depending on a, so this is for a greater than 0, and it's going to be this if a is less than 0, essentially. And you can see that in the graph because they're avoiding this line. The function is avoiding where y is 0 for some reason. And so it has to do with whenever you go and you try to find the intercepts of this function or any function. But when you go to try to find the intercepts, you have a y-intercept here. So you have a value when x is 0, but you have this asymptotic behavior when y is 0. So you can't really let the function equal 0. Just try it real quick. And this will lead into the logarithmic graph. But if you have f of x down here, let me get out of the way. F of x equal 2 to the x, and I found when the function was 0, when I plugged in 0 here for x, I got 2 to the 0, which was 1. But if I let the function go to 0, and you try to solve this thing to figure out the value for x, it's the exponent. It's the result of 2 being raised to the exponent x is 0. There's no exponent that you can raise to in order to get 0. Because you have, let's see, you have 2 to the first power, which is 2. You have 2 to the 0 power, which is 1. And then you have 2 to the negative first power, which is 1 over 2. So you can't, because you cannot, there is no, let's see, 2 would represent the base, x is the exponent, and then 0 would be the result. So we're trying to find the exponent that you have to raise to get 0. And that's the problem, essentially. You can't do it. And it explains a lot too, and it's a good segue into the logarithmic function. And the logarithm function, it has a stipulation that you cannot put a negative or 0 into the argument of a logarithm and produce, and it'll say domain issue, and it has to do with a lot their inverse functions. And so we might look at the logarithm graph next and see why, and maybe that'll make a little bit more sense. And so I was able to talk for 5 more minutes after I said I was going to stop. So no students in, no questions for me in the chat. So I am probably going to go ahead and stop there. And just remind everyone that if you happen to see my video and you know anyone that needs help with their math, or anyone that likes math, wants to do it, yeah, come hang out with me between 6 and 7 p.m. Central Time on YouTube, and we'll do some math. And if we'll go ahead and call it good for the day. And so another Monday in the wraps. And if you need help with your math, then go ahead and post in the chat, and I will get the notification, and I'll be able to work it in my spare time. So anyway, I am Professor L, and I'm going to go ahead and say goodbye. Thank you for watching my video, and I will see you again tomorrow. Bye.